Poiseuille's equation tells us how blood will behave depending on vessel size, system pressure. We learned that pressure is a type of energy that is one of the reasons for fluid flowing. But we didn't really define it. If we were to define it, we would say that it is a force per unit area. In a static liquid, pressure is exerted equally in all directions. In equations, you will see pressure represented as a capital P. Another way to think of pressure, or to remember pressure, is to think about when you fill your tires with air. The air pressure is pounds per square inch, so a force per unit area. And the air pressure keeps your tires inflated all around, not just one part of the tire. As true with energy, there also must be a change in pressure from one side of the vessel to the other side to cause flow. So we can change the energy gradient into also a pressure gradient. The fluid will prefer to flow from the side with greater pressure to the side with less pressure. The pressure in the vessels is created either by the heart or by gravity. Let's use gravity as a source of pressure for this example. This tube is at a slant. The end of the tube that is higher has more gravitational energy and more pressure. The tube at the other end has less pressure. Points in between create the gradient or slope of decreasing pressure. The change in pressure causes the fluid to flow from the tube that is up high to the low end. Volumetric flow rate, or sometimes just referred to as flow rate or even just flow, refers to the volume of fluid that passes a point per unit of time. If you're filling a 30-gallon fish tank and want to know how long it would take, you could calculate the flow rate of water from a hose. Using our definition, it would be a volume unit over a period of time, such as 2 gallons per minute. We could then use some quick algebra to estimate that our tank will be full in about 15 minutes. In ultrasound, the volumetric flow rate refers to the amount of blood flowing in vessels and typically uses milliliters per second. In equations, you will see this represented as a capital Q. Using our tube again, if we could just observe how much fluid passes by this one point, we would be able to calculate a volume over time. Looking at an adult's cardiac output, the total blood flow is about 5,000 milliliters per minute, which essentially equates to the body's total volume of blood circulating the entire body once per minute. Now we talked about viscosity as a force that causes blood to lose energy. Remember that viscosity is fluid's resistance to flow. Viscosity, though, is just one thing that can cause resistance. Another way to think about resistance is that it is a force on a moving object in the opposite direction. You may have also heard of this type of resistance called drag. Fluid resistance is measured in poise. Equations using fluid resistance uses a capital R. So we're back to our tube again, and resistance would be the force that is pushing this fluid in the opposite direction the fluid wants to flow. A lot of the resistance is going to come from the fluid itself and the object that it's flowing in. Let's look at flow rate, pressure, and resistance and how they all relate to one another. This is the equation that tells us flow rate. Flow rate equals the change in pressure divided by the resistance. Now that we know the equation, we can explore some of the relationships. Remember too that these equations are only true for long, straight tubes. The flow rate, or Q, will increase if the pressure change increases. In the first picture, the pressure change is small, therefore the rate at which the fluid flows is slow. In the second picture, the pressure change is large, and that causes the fluid to flow much faster. We see this when pouring liquid out of a container. The fluid comes out much faster if we were to turn the bottle upside down. This makes flow rate and pressure change directly related. Now, resistance goal is to keep flow from happening. So with this equation and knowing the definition, we can see that resistance and flow rate are inversely related. The flow rate is less when the resistance is high, and the flow rate increases when the resistance is low. Think about how honey comes out of a bottle compared to milk. So I know that this lecture is about Poiseuille's equation, and we're getting there. We just have one more equation to look at before we can. This equation goes into more of the physics regarding resistance. It tells us some of what we already know, that viscosity has something to do with resistance, but it's going to organize it a little bit more so we can understand other factors that change resistance. As a side note, I left out the units in this equation because A, it gets a little bit busy, and B, you don't really need to know this equation by heart. More so what I want you to know is what it represents, because it will help us understand Poiseuille's equation. So, resistance is equal to 8 times the length of the tube multiplied by viscosity divided by pi times radius to the 4th power. All right, so just stay with me here. Let's look at some of the big takeaways from that equation. First thing you need to know is that when the tube length increases, flow resistance increases. The second thing you need to know, if the radius of the tube increases, then the resistance decreases. And the last thing, if viscosity increases, then resistance increases. So let's combine what we learned about the flow rate equation with Q and what we learned about the resistance equation, R. If the tube length increases, that means resistance increases. That means the flow rate decreases. Secondly, if the radius increases, the resistance decreases, so that means the fluid would increase. Lastly, as the viscosity increases, the resistance increases, and therefore our flow rate will also decrease. Now that we have these principles in hand, we can learn a little bit more about Poiseuille's equation. So here I have for you Poiseuille's equation. Again, the units were left out of this presentation to really get to what this equation represents in the way of flow. Poiseuille's equation tells us that the flow rate is equal to the change in pressure multiplied by pi multiplied by the diameter to the 4th power, which is all divided by 128 multiplied by the length of the tube multiplied by viscosity of the fluid. You can see a lot of the elements that we've learned from the other two equations that led up to this point. Note that Poiseuille's uses diameter of the tube, not radius. So let's break this equation down into what we need to learn from it. Instead of using visuals, I've created this chart. This chart will help you to organize the relationships, not only in Poiseuille's equation, but many of the relationships that you'll learn during physics. So if the pressure change increases or gets larger, the flow rate will also increase. Think of that tube that had the large difference between one end of the tube to the other tube. That had a lot of flow coming out of it. The second thing Poiseuille's equation tells us is that if the diameter of the tube increases, then the flow rate will increase. So bigger tube, more flow can come out of it. That makes sense. If the length of the tube increases, then the flow rate will decrease. Again, that makes sense. You've got more surface area for that fluid to flow along, more resistance comes along with that. That means we just can't get as much flow out of a long tube. And lastly, if the viscosity of the fluid increases, then the flow rate decreases. Going back to that honey example again, honey is very viscous. It does not flow as easily as a thinner liquid such as water. All of these concepts have been illustrated before in this presentation. I suggest you check them out again if you need to. In a nutshell, Poiseuille's equation basically tells us that flow rate of fluid through a tube depends on how great the pressure difference is, the length and diameter of the tube, and how thick the fluid is. When we apply this equation to blood pressure is produced by the heart and gravity. The vessels vary in size depending on location, and blood can take on different viscosities measured by its hematocrit. Our blood vessels are not straight tubes, but the equations can give us a pretty good idea of how blood will behave.